All right, we are continuing with section 10.8. We are still looking at the power series. This is just a long lesson with a lot of information, so we're picking up with example 6. So we have a function f that's defined by the power series below. We want to find the domain of f. So when we look at this problem, it looks like we could use any value for x, but we're going to kind of rearrange it and think of it in a different way. So if I look at this series, the way that it's written, x to the k, this is the power series. But if I treat it as a geometric series, then it would be that ratio, that r up here to the k power. And okay, that's a geometric series. And if we recall the geometric series, the absolute value of that r has to be less than 1. And that's where the geometric series converges. So for us, instead of r for radius, we're going to use x. It's not a given fraction. We'll use the absolute value of x is less than 1. And if you think back to algebra 2, we have an absolute value inequality. So we'll say that x is less than 1 and x is greater than -1. So when we put this all together, -1 is less than x, which is less than 1. This is our domain. Okay, no problem. Letter B. We want to evaluate f of 1/2 and f of -1/3. So again, we're going to treat it as a geometric series. So if f equals 1/2, that 1/2 still goes in place of x, but it goes inside of the series. So this is k equals 0 to infinity. This is 1/2 to the k power. So that sum, and this is going way back, if you look at those formula sheets, the sum for your geometric series is a over 1 minus r. So for us, a is 1 over 1 minus 1/2. This is 1 over 1/2, which is 2, and that's perfect. F of -1/3, same idea. We're going to put that -1/3 in place of the ratio. Now my sum is -1, it's 1. 1 minus -1/3. So I have 1 over, add that up, that's 5/3, 5/4. This winds up to be 4/5. I'm not going to have time to edit that out, but you're probably thinking, hey, Mrs. Charlie, you're doing it wrong. So let's try again. It's a 1/3, not a 1/4. 1 over 1 minus 1, -1/3. There we go. So 1 over 1 plus 1/3, 1 over 4/3. So this becomes 3/4. Much, 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 much better. And then letter C, they want to find f by summing the series. So what we'll do is we'll use that same sum formula. A is the first value, or that coefficient in the front, which is in this case is 1 over 1 minus, well, what is that ratio r? And that's x. So I have 1 over 1 minus x, which is cool. Now, what does that do for us? I didn't write it in your notes. It puts it all together. So now what I'm saying is 1 over 1 minus x is the exact same thing as the power series, which would be the exact same thing as 0 plus 1 to the first power. Got stuck there for a second. Which would be exactly the same thing as x to the 0 plus x to the first plus x to the second plus x to the third plus x to the fourth, ... So this is 1 plus x, and then all those other things stay the same. This is called the power series. So what we're going to do in the future problems here is look at the 3 different representations, and these all mean the exact same thing. So I know that's kind of tough to believe, but let me hop over here to Desmos and show you something. Okay, so what I have are the series, and I also have the function. So let's look at this. Y equals 1 over 1 minus x. That's what we just said, that our series is the exact same thing as. So that's graphed here in red. I'm telling you it's the same as the series notation, this power series, this x to the n. So if I graph this, and this one's in purple, I'm going to say that L equals 1, right? So that's just the line y equals x. In fact, if I say L is equal to 0, x to the 0 is 1, so we have this horizontal line of 1. Now, L equals 1. All right, we've got the curve matched a little bit. Here's L equals 2, so I'm going up to x squared, 3, 4, 5, 6. If I hit play, it goes through slowly, but you can see that that purple curve is starting to match a little bit more each time. It's getting closer and closer and closer. Speed this up here a little bit. We'll bring it up here to 50. So 50 is an awfully good representation. Let me change this picture so maybe you can see through it. If I zoom in a little bit, there you go. You can see that they overlap. Now, they overlap as far left as -1, and they overlap as far to the right as +1. That's because that's where we said the domain was. We said that this only works between -1 and +1. So when you look, yeah, sure, my series is a really good representation of 1 over 1 minus x only between -1 and 1. So we're writing those in the same way. And if I take a second, give you one more in here, and I say that y is equal to 1 plus x, right? There's a purple line, kind of sort of works, plus x squared. Okay, even better, plus x to the 3rd. Even better, plus x to the 4th, even better, plus x to the 5th. Even better. Now, if I keep adding terms to this, all 3 of these things will match up. My drawn out polynomial, the 1 over 1 minus x, and the x to the n, they are all the same thing, but only between x equals -1 and x equals +1. That's as far as they're valid. I think that's a really, really, really cool, but that's visually what we're looking at with these. So I just recorded that whole part without actually recording. So I'm going to show you what I wrote down here. Good grief. I start with the power series. This function notation is equal to the series notation, which is equal to the expanded form. And that's what I just wanted to show you in the Desmos example. So what we're going to do is we're going to take whatever's sitting in the x position and replace all of the x's with exactly that. So for part A, 2x squared, don't worry about the negative because that's part of the problem. 2x squared goes in place of x. So I replace the x in the series notation with 2x squared. And in the expanded form, I replace those x's with 2x squared as well. Do you have to do that each time? You won't be asked to, but I want you to recognize the fact that those are allowed. You're allowed to do that. Now, in the series piece, yes, it's correct, but it's not finished. When it comes to series math rules, we like every single base to have its own exponent. It feels like we're undoing some of those things that we did in algebra. So this exponent goes to all of them. Everybody gets an exponent. So this is 2 to the n. And then this becomes x to the 2, and that these are multiplied. And this is the best answer for that series. Good. Now for letter B, we are set up. Okay, we have a 1. This 3 in the front, though, that really needs to be a 1. So how do I handle that? I divide every single term by 3. So we divide by 3, divide by 3, divide by 3. I'm left with a 1/3 in the numerator. I have a 1 plus x over 3 in the denominator. But we need the formula to have a minus sign. So I'm going to break up this plus, and I remember that minus and negative is plus. So this is a negative sign. So what I'll do is I'll go into x, and I'm going to replace x with that negative x over 3. And in the expanded form, I can do the same thing. I can replace all the x's with the negative x over 3. I just want you to know that you can do that, but that's not the focus of this example. Once I look at my series, here's my series. Again, we're like Oprah, everybody gets an exponent. So I'm going to break apart the numerator and denominator. Those each get an n. I'm going to pull off the -1 that has an n, x to the n over 3 to the n. Now, what makes this nice to have the -1 to the n? I can now automatically recognize it as an alternating series. So that's a good thing to do. But what we didn't talk about was 1/3. So this 1/3 really belongs in the front of the series. It belongs in the front of the expansion. Here it is in the front of the series and in the front of the series. But I don't want to leave it out there. What we can really do is take the 3 in the denominator and put it over here next to the other 3. And then I know that x squared times x cubed, if I use that property, right, with my exponents, this is really x to the 2 plus 3, which is x to the 5th. So here I can say that 3, which is really to the first power, times 3 to the n is 3 to the n plus 1. And that is the best series for letter B. Now for letter C, I didn't quite give myself enough space here. So let me erase all of this. This is a lot of information in a very short amount of time. So don't be afraid to ask me questions about what's going on. Okay, letter C, again, we're matching up with this power series representation of 3 different ways that we can look at it. This one has an x squared. So all I'm going to do is pull that in the front and I have 1 over 1 minus x. So everything else works perfectly. Here's x squared, here's the series, x to the n equals 0 to infinity. And this would be x squared times 1 plus x squared plus x cubed, ... Now, cool, you got the series, no problem. Well, I don't need the x squared in the series, but I can't leave it out there for the final answer. So this becomes n equals 0 to infinity, x squared, x to the n. Do we want to combine those? We could. I'm going to check your book in a second to see which one it goes for. X to the, and those would be added, n plus 2. And your book likes. Oh, that's right. Your book cheated and did one other thing with it too. This version works. Someone in class called this whole process extra. Yeah, the whole thing's extra. I don't have a better way to put that. Instead of starting at 0, they're saying, okay, let's start at 2, right? To infinity, and that this is just x to the n. You have to remember to do that. Cool if you can, but if you don't, it's not the end of the world. Right. Properties of power series. We can talk about the radius of convergence, and that's what we'll do. Actually, we did that a little bit, but now we're going to differentiate and integrate power series here. So I'm going to come back and I'll have to do that in another part of the video.